Hello folks, greetings from Chile. My name is Ruben Araneda and I'm from Chile, and I'm gonna try to talk to you a little bit about digital to analog and analog to digital conversion. Well, let's assume there's a guy singing in the microphone here. As we know, the microphone here turns the acoustic energy into an electrical representation of the sound. Well, then that signal is amplified up to line level. And in the audio interface, there's something called analog to digital converter that turns this continuous signal into a discrete one with a finite number of points. So each one of these blue dots can be represented as a combination of ones and zeros, and basically that's what a digital representation means. The reverse process is known as digital to analog conversion, and here we have our digital signal that goes to the digital to analog converter that converts it in electrical signal again. This drives a loudspeaker and you can hear the musical information contained in this digital signal again. Well, when we open our digital audio workstation, we have to set certain parameters that affect the digital to analog conversion. Here is one, sampling frequency, and the other one is bit depth. But why do we need 44,100 samples in a second? That sounds like a huge number. Well, let's see. Let's assume this is 1 second of audio, and that we have a sampling frequency of 6 times 4, 24 hertz. That's 24 samples in a second. Looks good here, but why do we need 44,100 then? Well, if you just take fewer samples than you need, you will end up with a problem called aliasing. That means that you're trying to represent this red signal here, and the computer represents this blue signal instead. That has nothing to do with the first one. It's a lower frequency wave. So what do we need to not have this problem? Well, there's something called Nyquist theorem of sampling that says that you need to choose a sampling frequency of at least 2 times the highest frequency you're trying to represent. So as humans can listen up to 20,000 Hertz, you need at least twice that number, and that's 40,000. Then with 44,100 you can represent a signal up to 22,050 Hertz. So it looks pretty safe to sample with that frequency. And nowadays, every audio interface has anti-aliasing filters, so you don't have this problem. Now let's talk a little bit about bit depth. What's the influence of bit depth in the sampling process? You have levels of, let's say, quantization, so the computer takes the value that's closer to the amplitude that's trying to represent. It's not exactly the point, because you don't have infinite levels, you have a discrete number of levels. So with 11 levels, this doesn't look so good, and we will end up representing a curve like this one. Well, as you see, with shorter bit depths, we get large error in the representation, and as bit depth increases its value, you get, well, no error is absolutely false, but you get close to no error. You will get error every time, so this picture is absolutely wrong. We can see that here in this picture too. We have 16 bits for representing this wave, and with 24 it gets better, and if we add to that a higher sampling frequency, with 24 you can get a very accurate representation. Well, that's all. Thank you for your time and attention.